Hello, welcome to our channel for probability and statistics. In this video, we will talk about the basics of hypothesis testing. So hypothesis testing is usually used to help draw a conclusion from statistical data analysis. So there are several examples. For example, a medical researcher may decide on the basis of experimental evidence whether coffee drinking increased the risk of cancer in humans. And an engineer might have to decide on the basis of sample data whether there is a difference between the accuracy of two kinds of gauges. And also, a socialist might wish to collect appropriate data to enable him or her to decide whether a person's blood type and eye color are independent variables. So in all of these examples, the scientist or engineer postulates or conjectures something about a system. In addition, each must make use of experimental data and make a decision based on the data. We have seen in each case the conjecture can be put in form of a statistical hypothesis and procedures that lead to the acceptance or rejection of statistical hypotheses, such as this comprise a major area of statistical inference. So this is an area of statistical inference if we do hypothesis testing in statistics. This is quite different from we have seen so-called confidence interval. So this is quite different, but they are related. So hypothesis testing is a very big area in statistics. So in this video, we only touch the surface of the fundamentals of hypothesis testing. So a statistical hypothesis is an assertion or conjecture concerning one or more populations. And the probability is a very important rule, of course, in hypothesis testing also, because the truth or falsity of a statistical hypothesis is never known with absolute certainty unless we examine the entire population. This, of course, would be not possible in almost all situations. So instead, people take a random sample from the population of interest and use the data contained in this sample to provide evidence that either supports or does not support the hypothesis. And the evidence from the sample, if is inconsistent with the stated hypothesis, this means we will get a rejection of the hypothesis. And it should be made clear that the decision procedure may include an awareness of the probability of a wrong conclusion. So, suppose that the hypothesis postulated by the engineer is that the fraction defective p proportion in a certain process is 10%. And the experiment to observe a random sample of the product in question. Suppose that 100 items are tested and 12 items are found defective. So it is reasonable to conclude that this evidence does not refute the condition that the binomial parameter p equals 0, because this is about 0.12. It's quite close to 0.10 in the statement. The sample is quite close to the statement, so we do not refute it. However, it also does not refute p 0.1 0.12 or perhaps even 0.15 we do not refute. So as a result, the analyst may be accustomed to understanding that rejection of a hypothesis implies that the sample evidence refutes it. Put another way, rejection means that there is a small probability of obtaining the same information observed when, in fact, the hypothesis is true. So this means when we reject the statement, this always we have the probability that we make a wrong decision, we make a wrong rejection, but we try to make this probability as small as possible. So usually we hope this small probability may be less than or equal to 0.05. So we will not go to too much detail here now currently, but this is quite clear. If we reject the statement, if there are lots of very big probabilities that it could be a wrong rejection, then we will not do this. We will do not reject, right? Because it's quite risk to reject. So if we reject this statement in the problem, we have to make this rejection error quite small. So again, for the same proportion defective hypothesis, a sample of 100 revealing that 20 defective items is certainly evidence for rejection Y. So if 20 of 100 is in defective items, this means in the samples there are about 0.20 in the probability. It's quite different from the statement 0.10. So, which means the probability of obtaining 20 or more defective is approximately 0.002 if this statement is true. So, which means with the resulting a small risk of a wrong conclusion. So in this case, if we get a 20 defective from 100 sample, if we reject the statement that the probability is 0.10, it's quite small risk that we make a wrong decision, we make a wrong rejection, right? Because this probability is quite low. If the probability of 0.10 is correct, then we get a 20 defective of 100 sample. This probability is only 0.002. So if we reject this is probability, the wrong rejection is only 2 of 1,000 chance. So it's quite low. This is what we want to see. So as a result of the firm conclusion, so we make a firm conclusion should be established by the data analyst where hypothesis is rejected. So we hope to see rejected, but we have to make a firm conclusion. We have a strong evidence. This is the basis of the rejection of a hypothesis. And in the structure of hypothesis testing, it's very important to know there are two types of hypothesis, H0 and H1. So H0 is called a null hypothesis, which refers to any hypothesis we want to test. So this is stated first. So we want to test this hypothesis. So this is called H0 or null hypothesis. And another hypothesis is the rejection of H0. So this will lead to the acceptance of an alternative hypothesis. So this is called H1, also called alternative hypothesis. And the alternative hypothesis H1 usually represents the question to be answered or the theory to be tested. So its specification is crucial, which means usually in scientific tests, H1 is more interesting statement we want to test. H0 is a null, which we hope we can reject. So this is usually very very usually circumstances in hypothesis testing. So we are more interested in H1. H1 may be a new device or a new theory, right? So we want to hope to see H1 is true. So based on firm evidence from the sample. And the null hypothesis H0 nullifies or opposes H1 and is often the logical complement to H1. So the analyst arrives at one of the two following conclusions. Conclusion 1 is reject H0 in favor of H1 because of sufficient evidence in the data, or fail to reject H0 because of insufficient evidence in the data. So we have to be very cautious about these two conclusions. We here say in favor of H1 and reject H0. And if we do not reject, we can say fail to reject H0 because of insufficient evidence. So note that the conclusions do not involve a formal and literal statement saying we accept H0. So the statement of H0 often represents the status quo in opposition to the new data, conjecture, which is stated in H1. So while failure to reject H0 represents the proper conclusion in our binomial example, the practical issue may be a concern that the historical defective probability of 0.1 no longer is true. And indeed, the conjecture may be that P exceeds 0.1. So in this example, we will form H0 is P equals 0.1 and H1 P larger than 0.1. So this H1 statement is testing for the one-side hypothesis testing. So now if 12 defective items out of 100 does not refute P equals 0.1, so the conclusion is we fail to reject H1 here. However, if the data produce 20 out of 100 defective items, so the conclusion could be we reject H0 in favor of H1. So H1 is P larger than 0.1. So in another example, a very famous example in jury trial, the null and alternative hypothesis could be H0 is the defendant is innocent, and H1 the defendant is guilty. So the indictment comes because of suspicion of guilt, and the hypothesis is H0, the status quo stands in opposition to H1 and is maintained unless H1 is supported by evidence beyond a reasonable doubt. However, fail to reject H0 in this case does not imply innocence but merely that the evidence was insufficient to convict. So the jury does not necessarily accept H0 but fails to reject H0. So this case is very important, very typical to say why we have to get a very small probability to make a wrong rejection. So if we have, for example, only 0.001 so wrong probability if we make a rejection of H0. So this is quite reasonable because we do not want to put innocent people into jail, right? So we have to make rejections probability, wrong probability as low as possible. And to illustrate the concepts used in testing a statistical hypothesis about a population, we present the following example. So certain type of cold vaccine is known to be only 25% effective after a period of 2 years. To determine if a new and somewhat more expensive vaccine is superior to providing protection against the same virus for a long period of time, suppose that 20 people are chosen at random and inoculated. If more than 8 of those receiving the new vaccine surpass the 2-year period without contracting the virus, the new vaccine will be considered superior to it when presently in use. And the requirement that the number exceed 8 is somewhat arbitrary, but appears reasonable, in that it represents a modest gain over the 5 people who could be expected to receive protection if the 20 people had been inoculated with the vaccine already in use. So here 25% is H0, a status quo, so current system, right? So if the current status is correct, so for the 20 people, about 5 will be effective, right? But now we get 8, so it's quite significant difference from this one, so we will accept that the new system is a better one. So we can essentially testing the null hypothesis that the new vaccine is equally effective after a period of 2 years as the one now commonly used. So the alternative hypothesis is that the new vaccine is in fact superior. And this is equivalent to testing the hypothesis that the binomial parameter for the probability of a success on a given trial is p equals 0.25 against the alternative that p larger than 0.25. So we can write H0 here, p equals 0.25. And H1 alternative hypothesis is p larger than 0.25 in this example. And the test statistic is a data calculation result from the sample data in the hypothesis testing problem. So the test statistic on which we based our decision is X. Here in this example is the number of individuals in our test group who receive protection from the new vaccine for a period of at least 2 years. And the possible values of X can be from 0 to 20, right? And we divide this into 2 groups. If the numbers less than or equal to 8, and those numbers greater than 8, all possible scores greater than 8 constitute the critical region. So this is the critical region, larger than 8, effective. So in our illustration, the critical region is the number 8. Therefore, if X larger than 8, we will reject H0 in favor of the alternative hypothesis H1. If X less than or equal to 8, we fail to reject H0. So this area will do not reject H0, and this area will reject H0. So in this simple example, we do not go further into the detail of how to calculate this critical region. We just give the basic process of a hypothesis testing. We will find the critical region, or say we find this critical value. Critical value usually on the right side called critical region, and on the left side we do not reject the hypothesis. In critical region, we'll reject the H0, we reject H0 and accept alternative hypothesis. We'll accept H1, right? So this is the basic process of a hypothesis testing we have talked so far. Thanks for watching.